To understand the basic imaging sequence, to understand how basic information is spatially encoded with MRI, we need to deal with the question on what is the effect of the gradient on the signal, and how do we make, for example, the signal maximal with under the influence of a gradient. Let's first look at the signal as a function of time. So we have an object, we have a gradient along y here. Now I'll use y just because it pleases me. We don't always have gradient along x. So we have the magnetization along y. This is the equivalent equation that we had on 2 slides earlier. If we now look at this equation, then we can see that for this is our complex numbers. So again, the real part is x, the imaginary part represents the y component of the magnetization or of the signal. And if we look at this equation here, then we can see that at time 0, this term is 1, and then we are getting the signal as a function of time is the magnetization, it's constant. However, if we apply the gradient and we look at times bigger than 0, then we have increasingly one magnetization vector corresponding to a positive y position moving in one direction, the other magnetization rotating in the other direction or in a complex plane. Now the complex numbers, according to their position along y, will have a different phase, and they will no longer add collinearly, and this is called dephasing. So our signal is maximally at the beginning. So let's look at a gradient, and I will here take a gradient along y. I'll have it at 0, then I'll have it at a negative value, and then I'll put it to the same value that is positive here. We're going to consider these 3 time points here, where we switch the current in the gradient coil, and we're now looking at the phase of the magnetization, that is this position, this term here, at the over time, starting here at time 0, where we have this magnetization here in phase. So we're looking at the phase, that's this term here just before the I. So if we take one position along y, then we're getting a phase that evolves this way. I will plot here in terms of position. We have y and x. So we'll have this position. We're looking at one position in y, so we'll take this position. Y is small, and here we have all the magnetization at time 0 are in phase, so they all have the same, they're all collinear. Now we'll take the next position in y, which is a bit further away, so GYY is bigger, so the phase is bigger, the slope is bigger here, and here the slope is inverted because we invert the sign of GY. For the third position, we have this, and we'll just continue equidistantly. That's the 4th, and that will be the 5th here, the 6th, this position, and the 7th at this position. And now what we see is, because here the slope is proportional to position, and here the slope is also proportional to position, but the slope here is equals to the negative of that slope. So since this time here equals to this time, and so we'll have a point here where all the magnetizations are again in phase. They have a phase of 0, and this creates a maximal signal, and that's what we call echo formation. And what you typically would see in the computer, the digitized signal that's observed is something like this. It's an echo. That's what is called an echo. So if we look at the phases, we have dephasing. Dephasing means that the magnetization vectors spread out in the transverse plane. They no longer add collinearly, so signal decreases. And then when they all come together again, we call this phase of the evolution rephasing. And so if we look what happens over time, then we have rephasing. Here we have echo, all is in phase. Now we have dephasing. You can see they're not in phase. Now they are reversing their orientation, and they are in phase again. So we have dephasing, the magnetization vectors spread out. Then they come together again. Here they're again together. And this is happening if the area of the gradient here equals the area of the gradient here, or if the integral, the sum of all the gradient over time here, equals to 0 in more general terms. So if we have equal area, positive and negative, then we have echo formation. And this time here, from here to here, is typically called the time of echo, or echo time TE. And if we go on afterwards, then of course we have dephasing, and now the vectors are all dephased and they are no longer producing a measurable signal after a certain amount of time. So if we call this time here tau, then from here to here tau is equals to TE half in our particular example. So we can write the magnetization at this time point is equals to the magnetization, transverse magnetization at time 0 times the phase term, and this is now being done by integrating along y. We have the minus here because the gradient is negative, so Gy is the magnitude of the gradient. The gradient during time t, and time t is this time here, that denotes this time here. The gradient during time t, the signal during time t is proportional to transverse magnetization. That's the sum of the transverse magnetization over the object. So we sum over along dy, it's the magnetization along y at time tau times this term here. Here it's now positive because we have changed the sign of Gy. And now we'll put this together. That is, we'll insert this into here. The magnetization at time tau is proportional to this. We'll put this in here, and in the equations I have just assumed that they are equal. This is really a proportionality. Then we have the magnetization at time 0 here, the transverse magnetization times these two terms. So this term we can understand, that's the magnetization right after the RF pulse, and here what about these terms? So I will look at these two terms and I will rewrite them into the exponent, and so we now have e to the I gamma Gyy times t minus tau. And so this means this term here, if we look at this integral with the same argument that we had here, if this phase term is 0, then we have maximal signal, and that is happening when t equals tau, and so we have echo formation, and this is given at this point. So this is what is being observed. Okay, so this is a graphical, mathematical demonstration that in a experiment, simple experiment where we have a gradient that's negative and then we put it to positive, that after 2 times this period tau, we have echo formation, how it occurs. Now this is not easy to understand, and one has to really think about it, how to visualize that, and I'm going to now try to take a different approach. So let's try to look at echo formation here under a different viewpoint. And what we're going to do here is we're going to suppose that our magnetization vectors are represented by the position of our magnetization vectors are represented by a tortoise here and a hare. And we're going to make them run on a circle because they're magnetization vectors. The tortoise and the hare represent the tips of magnetization. And they're going to be running at a certain velocity, that is, they are going to have, this velocity is given by angular velocity times the radius of this circle. So this is like track and field. Instead of having an oval, we're running in a circle. So at time 0, they're both at the same position. Now we'll have the hare running fast in one direction and the tortoise running slow in the other direction. So that is the precession of fast and slow magnetization. At time 0, they're both up here. So they're here. And now we'll have them run for a time of TE over 2 seconds, or milliseconds if you want. Since the hare runs faster, he will have run a bigger distance than the tortoise, which is much slower. And we'll here, for simplicity, we'll assume that the tortoise is running in the opposite direction as the hare. So tortoise is run until here, the hare is until here. They have run in this direction. Now, after t over half seconds, we give the command to reverse the direction. So that is a 180-degree turn. We're telling them, instead of running as you have been running, now you run in the opposite direction, still on the circle, but with the same velocity. So this is 180-degree turn around, and now we're running back to, we're letting them run again for the same amount of time. Now the distance that they're going to run on the circle for the same amount of time, since they are running at the same speed, the distance traveled is going to be the same but in opposite direction. So after time te, after te seconds, they're both going to end up again at the same position, like this. Okay, so is this now clearer? So we have had a tortoise slowly running on a circle and a hare running fast on a circle. We've said these represent the tips of the magnetization vectors, of two magnetization vectors. Now the argument that I've made here is assuming two different velocities for tortoise and hare. So two different precessional frequencies. That's the omega here. Now we can imagine what we have in our organ of interest. We have hundreds, literally hundreds of thousands of different tortoises and hares, and they're all running at different speeds in different directions, etc. I have made no assumption whatsoever on the specific circumstances on the speed of the tortoise or the hare. So this is valid for any two pair that we compare, that they will arrive after time te at the same original position that they had. So this is in general the case. The only thing that we've imposed is they're always running at the same speed, and after half of the time they reverse the direction. That's the influence of the gradient. And so the time te is also called the echo time, and that's what we will refer to very often from now on. So I hope this is now a bit clearer how echo formation is done under the influence of a switched gradient, where we change the polarity. There we changed, with the polarity of the gradient, we change the direction in which the magnetization vector at a given position is precessing. To understand better the diagrams I'm going to be showing from after this slide, I have to address one question, and that is it important when exactly a gradient is being applied? What is its influence when the gradient is being applied on the signal? We'll consider here an experiment where we have a gradient along x. It goes from negative to positive. Doesn't actually matter exactly what we're doing here, but we'll take the same example as we had before. So if these two areas are equal in magnitude, then we will have, at this time point, we will have echo formation. And this time here we call the echo time te. And we will denote here the start of this time counting here as the time tau. And this time here will be 2 tau. Now I will take a gradient along z, and I will switch it just before the green gradient along x. So this gradient here is applied just before. It's turned off at the time tau. This is its effect on the phase. So that is what we call the sequential application of two different gradient orientations. Now we'll take the same experiment again. We have the gradient along x. We have echo formation. And we'll apply now this same gradient along z, but we will apply it at the same time as we apply the negative lobe of the x gradient. So everything is identical except the timing for the red gradient. Here's again the echo time te, and this is what we call the simultaneous application of the gradient. And now the question is there going to be a difference on the echo that we record here? Does it make a difference? Can we tell from the signal that we record here whether this gradient has been applied here or whether it's been applied here? So let's look at the magnetization in the left example after time tau. It's given by the magnetization at time 0 times e to the gamma gz z times tau. This is the effect of this gradient here. And on the right side, the magnetization at time tau is still the magnetization at time 0. We have not done anything to the phase of the magnetization. This is always done in the rotating reference frame, so we don't consider the effect of B0. It makes it easier to write less terms. At times 2 tau, we have the magnetization at times tau here that we start with. We're always talking about transverse magnetization, of course, times e to the minus gamma gx times x times tau. We have here the time here from here to here is tau. So that's the magnetization at times 2 tau. And we can now substitute m of tau in magnetization at time tau into this equation here. We get this term that is over here. On the right hand side, the magnetization that is now recorded times 2 tau is the magnetization at times tau times e to the gamma gxx plus gzz times tau. And what we have used here is just a general term that the magnetic field, the B0, in the presence of a gradient, now we take the B0 out because we're in a rotating reference frame, but the variation of the magnetic field in space is given by gamma times the scalar product of the gradient vector times position. And here the gradient vector has components along x and z. So we can rewrite this now. M of tau is m0. We'll write these terms here and we'll split them according to x and z. And now what we will notice is this term here and this term here. Upon inspection, we notice that these two terms are identical. So the magnetization M0, M of 0 in both cases is the same. We start out here. We don't know yet what's happening, so the magnetization at that point has to be the same. The conclusion here is the application of two gradients that are orthogonal, say x and z in this particular example, could be any two directions, simultaneously or sequentially, doesn't matter. It produces the same phase for the transverse magnetization subsequently. So what this means basically is that we have the magnetization described here or described here. These two diagrams, in terms of what's happening to the magnetization, the transverse magnetization, to its phase, are identical. So if we have difficulty understanding the diagram on the right, we can always suppose that this on the left is happening. So at time te, the magnetization is given by the magnetization at 2 tau times this term here. And we can write this now by putting the magnetization of 2 tau into this term here. And then we get the magnetization of time 0 times e to the I gamma gz times z times tau. The effect of x, of course, the gradient is nullified exactly at te. So we only have the influence of the z gradient. Okay, so this is just to bear in mind. If you see the diagram where the gradients are in two different directions are applied simultaneously, if this creates conceptual problems, you can always think of that you have a much more space to draw them sequentially, like on the left-hand side, if that is easier to understand. I didn't do it because it makes the display of what is to come very crowded and very difficult to read. So now I will introduce the basic elements of the so-called gradient echo sequence. We'll start out, of course, with a RF pulse. This is what we do with the RF pulse. We flip the longitudinal magnetization by alpha degrees into the transverse plane. We start out with a magnetization at time 0, which is just the z component before the RF pulse. This defines one time point here. We will now have the frequency and cogradient. We have it negative and then positive. So that's essentially the situation we've been discussing in the previous slides. The negative area here equals to the positive area here. That when this is matched, then we have at this time point we have echo formation, and that is the echo time. So this is what we observe here. We have the signal as a function of time, and we have echo formation exactly at echo time. Now, this is a experiment that we've discussed. Implicitly, I have not drawn the RF pulses. Now, we want to do slice selection, and as we've discussed earlier in the course, this is done by applying at the same time as the RF pulse is to apply a gradient, and here we'll call this gradient the z gradient. So what this alpha pulse now does, alpha degree pulse, it will flip the magnetization by alpha degrees into the transverse plane at the Larmor condition defined by the radio frequency of the RF pulse. And we have a positive gradient afterwards and a negative gradient subsequently. Now, why do we have to deal with this gradient switching in the slice selection? Wouldn't it be just enough to turn on the gradient, we'll do the slice selection, and we're done with it? Well, the situation is also here. You can see that previously we have assumed that the gradient switched on instantaneously, and here you can see in this gross exaggeration that the gradient switching takes some time. And this has to do with the question, why do we have to have echo formation? We have, after the RF pulse, we have the gradient is on. So the magnetization is in a transverse plane. It will spread out. If we turn it off, the magnetization will stay spread out. If it's spread out, then means it's spread out according to the position along Z. They're no longer, the magnetization vectors no longer add collinearly, and therefore the signal is reduced. What this negative gradient here does, it takes into account this dead time here that we have and makes them run in the opposite direction magnetization vectors, and with a matching condition they will be all collinear and we will have maximal signal. So let's look at the effect. If we don't turn on this negative gradient, the signal is given by the transverse magnetization across the slice times e to the I gamma gz times z over tau integrated over z. So this term with time will eventually go to 0. That's dephasing. So we can not record the maximal signal. The signal decays, and it actually decays rather fast. It is a decay that is almost like a FID. It's not T2. It's the effect of the dephasing from the different positions along the slice. So, and we can rephase this term. We can make the magnetization collinear again by a rephasing, that is by applying a gradient with opposite polarity. Here it's drawn negative, and this leads to echo formation. And if we write this in general terms, then for the slice, if we integrate over the slice, we have the magnetization times e to the, in general terms, the phase is here given by phase of time. The phase is given by the integral of, for a given position of gamma gz t over time. And we want this to be maximal. That's what gives us echo formation. So this phase term, this term must be maximal. And there is actually a nice condition for that, and that is that the integral of the gradient from 0 to a certain time of the gradient is equals to 0. So that basically is what's depicted here. This area equals to this area. That's the same thing as saying this integral over time is equals to 0. That leads to echo formation. So in this example we have the slice select, the slice orientation, the slice gradient is perpendicular to the read or frequency encode gradient. So x and z are presumed to be orthogonal. Whether we call them x or z or y and z and so on, whatever we call them, doesn't matter. That's the main condition here, is that they're orthogonal. Of course, at some point the ADC is opened up, the data is sampled, that is done here, and then the recorded signal that is recorded in the scanner looks like this. What is crucial here is we don't just record from the maximum of echo and then onward, we record also the first half of the echo. This is done because this is at very little cost of time. One can increase the sensitivity because there's more data points that are being sampled. So this is your basic imaging sequence, the basic elements, and this describes what's happening every TR seconds. That's your basic imaging sequence.